Okay, I hope you all can hear me. Can you all hear me? Yes or no? Can someone answer me, please?
Yes.
Okay. So I've drawn the element now, right? And I'll zoom up because I need or you know what? I'll bring this up here so I use less real estate. Okay. So the element now is oriented in such a way that is 30 degrees clockwise, right? It's 30 degrees clockwise, as you can see. And right, and then we did call this our, this is our now our Y30, right? And this is our X30. From X30 to Y30, we know that this is 90 degrees. That's why on Mohr circle is when I drew the straight line Y30, I say directly opposite is X30. Okay, now I want you to focus on Y30 first, okay? So you look at Y30, right, on the element, okay? So you draw a horizontal line, and this is your point Y. You draw a vertical line, this is your line for X, right? And this is rotating the element by 30 degrees, right? 30 degrees, right? So Y, right? Y rotate by clockwise. This is 60 degrees, okay, to Y30, right? On the element is 30 degrees, right? So that value is what? Is tensile, it's compression minus 9.509. So the normal stress is usually very easy, right? So it's equal to minus 9.509 megapascal compression. Now, I want you to look at the shear. Is the shear of the element, if the in the shear, is the element going clockwise or anti-clockwise? Can someone tell me? Clockwise or anti-clockwise at Y30? Look at the Mohr circle. It's rotating what? What is this direction?
Clockwise.
It's rotating in the clockwise direction. So for Y30 to rotate clockwise direction, the shear has to be coming down this way. Can you see that, how I draw the shear on the bottom right hand column, right? The Y30 with the shear in this direction, right? The element will rotate in a clockwise direction. Okay. So let's look at X30 now. Okay. So X30, we know that it's going through compression also. All right. And the compression now is 0.491 minus 0.491. Right? Minus 0.4. So if you look at the at X30, the rotation will be what? Anti-clockwise, right? So for it to rotate anti-clockwise, the shear has to be in this direction. That is the shear direction. So this is a bit more that we have done. What we have done now is to, there's a shear configuration. The example that we did before, like this one that I'm circling now, there's no shear because it's at its principal plane. Now this one, 30 degrees rotation, it is not at the principal plane. That's why you have the shear direction. Okay. So anything else I like to, yeah, you have to get it right. So the shear is based on the rotation of the element. I'm thinking, did I miss anything out from here? No, I can't think of anything else. Okay. Okay. So this is how we deal with Mohr circle in 2D. Okay. And this is the most extensive that you'll do. So you can locate the points from the element to Mohr circle, and then from Mohr circle you go back to the element, and you can calculate any stress state. Someone has a question, you can ask me now. Anyone? No? Okay, we are next going to 3D Mohr circle. Okay, so this is 2D Mohr circle. Now, 3D Mohr circle, it is still circle. Okay, you don't think, oh shoot, 3D Mohr circle is going to be a sphere. No. 3D Mohr circle is still going to be a circle. It's only more circles. Okay, it's only now it's no more one circle. Now it's 3 circles. Okay, now it's 3 circles. Okay. So we are going to look at 3D Mohr circle now. Okay. Okay, we are going to look extensively at 3D Mohr circle. So with 3D Mohr circle, now we are no more working on an element. Now we are working with a cube now. Okay, now we are working with a cube now. Okay, and I want you to I want to show you how this. So now our transformation x, y, okay, and then we have a z. Okay, so I'm going to draw my element, and the element is deliberately drawn this way. Okay, deliberately. Okay, it's deliberately drawn this way. Okay, so you have stress. Right, so over here is stress in the x direction, stress in the y direction. Okay, stress in the z direction. Okay, then we have another plane. So you have 3 normal stress. You also have 3 shear stress. Okay, so the shear stress. So this one we have just drawn. So shear in the x, y, and this is also shear yx. Okay, and then the other shear is in this direction. And this direction is shear. The plane is intersecting the zy. And this is equal to shear yz. And the last shearing direction. Hey, wrongly drawn. And the last one. So this is shear. So this is the z x, and this is equal to shear xz. Okay. So this surface over here. Okay, this surface over here. So we altogether we have 3 planes, 3 known planes, or 6 planes, but they are repeated, 2 repeated. So it's 3 planes, unique planes. Okay. So over here, right over here, this is our YZ plane, right? This surface over here is our XZ plane, and over here, this is your XY plane. Okay. So what I'm going to highlight to you is this. Okay. XY plane is known as our in plane. YZ plane is known as out of plane. And XZ plane is known as our out of plane. Can someone tell me why? Why is our XY plane in plane our YZ and our ZX is known as our out of plane? Anyone? What trend can you see? By the way, you cannot get this from the textbook, okay? Textbook won't tell you that. They so-called assume that it's known. So what can you tell that is XY plane that's different from YZ and XZ beside the orientation? Why XY is in plane? Any idea? Anyone, please? Anyone? So you can see that it's based on the largest what? Area drawn. Okay, I've been trying to read textbook. Why is this in plane and out of plane? Okay, it's so-called it's understood. Okay, it's not understood. Okay, so it is in such a fact that whatever plane you draw the biggest surface area, you call it the in plane. Those that are smallest area, you call it what? Out of plane. Okay, so yeah, textbook says that it's known, but it's not well known. Okay, so I'm going to write that when the orientation of the element is such that shear xy is equal to shear yx, comma, or and shear yz is equal to shear zy, and shear xz is equal to shear zx. They're all equal to 0. When everything is called to 0, then the element is at the principal plane orientation. Okay, principal plane orientation. Okay, so there are 3 conditions that we are going to look at. So the purpose of 3D the purpose of doing 3D element or 3D Mohr circle is to determine the principal stress is to determine the principal stress and how to select the proper workpiece material. Okay, so that's important. So later on, probably not today, next week, we will analyze the structure in 3D, and then we select the material based on 2D tests. Okay, so that's what we're trying to do next week. Right. So now let's look at 3 conditions. Okay, let's look at 3 different conditions on 3D Mohr circle. So condition number 1. Okay, so on a 3D Mohr circle, now the transformation is always the same like what I've just drawn initially. Okay, so I'm not going to repeat drawing the transformation. So this is our element. Excuse me. So in our element, so we know that this is our stress X, stress Y, stress Z. Okay. So condition number 1 is where condition number 1 is where stress Z is equal to 0. Okay. Stress X is greater than stress Y. Okay. And both are positive. Okay, both of them are positive. Right, so from here, you can see that this is your XY plane.